Let's find the parametric equations for the tangent line to the curve with the given parametric equations at the point with the indicated value of t. So the curve is defined by x equals t, y equals t squared, z equals t cubed, and we want to find the tangent line when t is equal to 1. Let's start off by writing this equation as a position vector. So the position at a point on our curve for any value of the parameter t is given by t for the x component, t squared for the y component, t cubed for the z component, and we want to find this for the value of t is equal to 1. Now, what are we trying to find? We want to find an equation of the tangent line. At t equals 1. Let's look at a qualitative sketch to wrap our minds around this problem. Suppose we have a curve that represents a vector-valued function. This curve is described by a position vector for any point on the curve, r of t. If we have a point on the curve such that t is equal to some value, at that point on the curve, there is going to be a line tangent to the point on the curve for t is equal to 0. We want to find the equation of this tangent line. Now remember, we could use the parametric set of equations for a line. The parametric equation for a line has an x-coordinate given by some x-coordinate for a point on the line. We'll call this point x naught on the line, plus some constant a times the parameter t, where a is the x component of a vector that is parallel to the line. So that vector that is parallel to the line has an x, a y, and a z component, and I'll qualitatively represent that vector in our sketch. This is our vector v being parallel to the line at that point A. Now vector v then is parallel to the tangent line at that point. So the x-coordinate being equal to x naught plus at, well, the a comes from the x component of the vector that is parallel to our tangent line at the point. The y-coordinate of a point on the line is given by a known given point, y naught, plus bt, where b is the y component of our vector v, which is tangent to the line at the point we're interested in. And the z-coordinate is given by the z-coordinate of a point on the line plus ct, where c is the z component of that vector v. With this said, we are looking for a vector v that is parallel to the line at the point A, or in other words, tangent. So this would be a tangent vector on the curve at the point we're interested in. And we also need a point on the line. That point on the line is going to allow us to come up with this parametric set of equations for our tangent line. Well, we could get a vector that is tangent to the curve at the point we're interested in, the tangent vector, by taking the derivative of our position function. So the tangent vector t, which is also given as, or also referred to as, the velocity of our curve at a point, vector v, is equal to the derivative of our vector function with respect to the parameter t. This means that we just have to evaluate the derivative of our position function, or position vector rather, with respect to t. So vector v then is just the derivative of each of the components of our position vector. So the derivative of the x component with respect to t, the derivative of our y component with respect to t, and the derivative of our z component with respect to t. Our velocity vector ends up being 1 for the x component, 2t for the y component, and 3t squared for the z component. Evaluated at the point t equals 1 results in our velocity vector having components of 1, 2, and 3. This velocity vector is a tangent vector, tangent to our curve at the point t equals 1. Now we only need to find a point on the curve before we could set up our parametric set of equations for the line. So a point on the curve can be found by taking our position vector and evaluating it at t equals 1. This would be 1, 1, and 1, as you could see when we substitute 1 in for t for our position vector. Now we have a point on the line, which I will label this point r sub 0. We have a point on the line. We have a vector tangent to our line at that given point at the value t equals 1. So our parametric set of equations of a line can be expressed compactly as a position vector is equal to some other position vector r naught for a known point on the line, plus the velocity vector, which is a tangent vector to the line, times t. So this then is x, y, and z is equal to our known point on the line, 1, 1, 1 being a position vector that locates that point on our line, plus the velocity vector at that point, 1, 2, 3, times our parameter t. This now yields our parametric set of equations that describe this line that is tangent to our curve. The x-coordinate is given by 1 plus 1t. The y-coordinate is given by 1 plus 2t, and the z-coordinate is given by 1 plus 3t.